Okay, so today, first we're gonna have a review like always. So I'm gonna do some review kind of based on what's gonna be on the quiz today, kind of like we did last week. And let's look at our schedule today. Okay, so we're gonna start with review. Sorry, my video is bugging out. Okay, so we're gonna start with review. Also, I'm gonna go over review and quiz feedback. And then we're going to continue on with what we did last time, which was element by element operations. So we're going to talk about multiplication with matrices and then division with matrices. And then we might be able to start matrix operations, which are different than what we've been going over last week. And then we're going to have the quiz. So before we do that, I want to go over how to view quiz feedback. So I thought I sent an email out on Monday for what was going to be on the quiz, but apparently didn't send out correctly through Canvas, so I sent that out yesterday. But in my first email, I kind of talked about how you could view quiz feedback. I think I actually also did yesterday. Let me check really quick. Yeah. So if you want a more visual, guide on how to view your quiz feedback, basically, you're going to go to quizzes.
Oh,
And
wait,
then,
Patrick. Just quick comment. If we go to Canvas, we actually could see the announcement, but I don't think you did send it in through email.
yeah, Canvas, it should, if I have an announcement, you should get an email unless you changed a setting for your profile.
Hmm.
Because I
Uh,
received the email too myself, actually. Okay, so if you want to view your quiz feedback, you're going to go to quiz 1. And don't worry if it says it's late. You see it says it's submitted at 3:45. I don't know why Canvas says that it's late. It's not late. But again, you're going to go to quiz 1, then submission details. And then you'll see your quiz kind of pop up here. And of course, this is like a dummy student account that I have here, so there's no answers. But if you had an answer, I might give you feedback below your answers, so it'd be like right below here. So make sure you look at that. Okay, so that's that. And so now I also want to quickly touch on basically organization for your Matlab code. So I've noticed from some students, and I did this too, that it seems like some of you are a little like I don't want to say unorganized, but some of you might put your Matlab code just in like your documents folder here, and I know when I was in my first few years for college, it was like totally messy. I had like all of my class files in there. But for us, we're going to be making a lot of MATLAB scripts in this class, so you want to make sure that you're organized. So for me personally, I have a folder just for, in this case, grad school, and then I have it semester by semester. And you can see the path that you're in up here. So, you're probably in somewhere from your documents, and then you have your school directory. So, I have one for this class as well. And then I have it kind of broken down, in this case, by lectures. And then we'll go here, and then MATLAB files. And then I can see all my files here. So, again, I saw some of you, and this is just, it'll be easier for you to find script files. I saw some of you even are currently in a directory when we downloaded that add-on in like the very beginning of class called MATLAB Schemer. And that's in a really random kind of place in your computer. It's in like this subfolder for MATLAB add-ons. In fact, I'll actually show you really quick where that is, because again, if you have a lot of your files in that folder, it would be kind of hard to pin down where that is. So let me go to Schemer. Okay, so now you see, again, some of you have like script files in this folder, and this is located, it'll be similar on your computer. It'll be in your like users directory, and then MATLAB add-ons, and then collections and MATLAB schemers. So that's a really random place, right? So if you currently have files in here, I would recommend moving them into somewhere that's more accessible, kind of like, something similar to what I have. just to keep everything, localized in one place and you know where to find it. But anyways, that was just kind of an aside, but it'll help you stay organized throughout the class. Okay, so review. I'm going to basically, for the review today, I'm going to go over a few of the homework questions that we had. And don't forget that if you didn't submit your homework yet, it is still due today, even though I gave you the solutions yesterday. So make sure you submit them. So the first thing that we'll do is question 2 on the homework, which was for appending arrays. So this will be, for the quiz today, some of the techniques that you're going to have to use on some of the questions, you're going to have to use appending arrays. Okay, so there's a question on how we can move the files. So if you want me to, I'll maybe make a video actually for how to move your files if it's in that different directory. So I'll make that sometime today and then I'll post it. Okay, so again, appending arrays, that's going to be one of the techniques that you have to use on, I think, like 2 questions or something today on the quiz. So, okay, you think you have everything in the schemer folder. Okay, so yeah, I'll basically make a video where I also have some files in that schemer folder, and then I'll show you how to move it to somewhere that's more accessible. Okay, so homework 2, problem 2. So the first thing that we wanted to do was create 2 different row vectors. So the first one is creating row vector R. And, you see here that we have basically a step size that looks, that we can figure out quite easily for what it is. So we know the starting point, we know the end point, and we can calculate or do it in your head, right? The step size that we need to have here. So for this, I'm going to use the colon operator. So I'm going to do r equals -23. And then we're going to do a positive 7. That's our step size. And then we're going to go to 103. All right, so I'll run that. And then we have that row vector. And even without typing in the length command that we have in Matlab, you can see in the workspace that the length for this vector is 19. So we have 19
Patrick?
elements in this vector. Yeah.
I think I'm getting confused with numel and length when it comes to when it comes to creating a row vector or column vector with matrices. So numel is it only bringing the number of elements, or is it like yeah.
Yeah, so if you have a vector, so either a row vector or a column vector, numel and length are going to do the same exact thing. But the difference comes in when you have a matrix. So if you have a matrix, numel is always going to give you the absolute amount of elements in that matrix. But if you use length, it's going to see, are there more amount of rows or are there more amount of columns? And whatever is higher, it's going to tell you the amount of rows or the amount of columns.
So length and numels are pretty much, well, like line space, numel, length. There's pretty much same thing, but it's just really depends what application you use, right?
Yeah. Length and numel are the same for vectors, but a little different for matrices. In linspace, that's used to create a vector.
Okay, all right.
Yeah. So we're actually going to use linspace right now. So we have to make this row vector S, and of course you can again calculate the step size if you wanted to, but it's really kind of a nasty looking step size number. And you were given the instruction that we need to make this row vector S that has the same length as R. So we know the starting point for S, which is 13, and we know the ending point for S, which is 56. And we also know the length that we should have for this vector, since it's going to be the same length as the vector that we just created, R. And that length was 19. So again, numel for a vector, that's going to be the same as the length function, and they're both going to be 19 for row vector R. So we can again use linspace for this vector S. So we have linspace. I'm going to put in the first value that we want to have, that's 13. I'll put in the last value, that's 56. And then we'll put in the length that we want, which is 19. Okay, and then you can see in the workspace, just to like kind of verify that both of these have a length of 19. Okay, and then what we want to do is from these row vectors, we want to create a matrix T that has dimensions of m by 2, where m corresponds to the length of the vectors r and s. So I had a few questions on this question. So I know that that line right there can kind of be a lot to take in. But basically, we want to use those two row vectors that we just created, and the amount of rows that we're going to have in our matrix T, that should correspond to the length of our vectors. So basically, we should have a matrix that has 19 rows and then 2 columns. So we created 2 row vectors, so we're going to have to use the transpose operator to make them column vectors. And we're also going to use appending technique, so we can append one of those column vectors to another, and we can create our matrix T. So I didn't specify which matrix should be, or which column vector should be in the first column, and which should be in the second. So in this case, that wouldn't really matter. I would be more specific on the quiz. But what we'll do here is T, and we want to make a matrix, so we're going to use our brackets here. So we're going to do T, and for me, I put in R. That's going to be the first column vector that we have here. And again, we want to transpose it, because currently it's a row vector. But again, we want to make a matrix that has 19 rows and then 2 columns. So we have R transpose, and then I'm going to put S transpose. Alright, so now if we run this, we can see over here in our workspace that we have a matrix T that has a size of 19 rows and 2 columns. So if you want to see it in the command window, then there we go. Okay, so again, for today's quiz, you're going to be using transposing techniques and appending techniques at a few points. Okay. Alright, so we're going to do number 7 as well. For part of today's quiz, you're going to be doing array addressing. Okay, there's a question. Why couldn't we make the second one using colons? You could have used the second one using colons as well. I personally think it's easier to use the linspace command because if you want to look at, if you want to use the colon operator to make that row vector S, you need to specify the step size that you have. And if you look at this step size, it's a little nasty. You could have calculated it, but it's not like a nice whole integer. So it's easier just because we know the starting point and the end point, and we knew the length that we wanted for this vector S. So that's why I used the linspace command. But you can use, again, the colon operator as well. Okay, so problem 7. Okay, so we had to make this matrix D. So we'll do D equals -2, 10, 34, 77, 3, 5, 15, -7, 12, 66, 303, 12, 33, 29, -11, -87. Let me put this down here. Okay, so there's our matrix, and we can pull it up here as well. Alright, and then from this matrix that we have, we're going to be doing some array addressing. So we have four parts here. So for the first part, we want to specify the element that's in the third row and the second column. So we want to look at the third row here in the second column. So we should be getting an output of 66. Okay, so I'm going to call this A. So I want to reference the matrix D, and I want to go into the third row. So remember that we always do row, comma, column. So we want to first specify the row, so that'll be row 3. And then we want to look at the second column, so we'll put comma 2. Alright, we run that, and then our output is 66. So that worked, just like we wanted. So that's a pretty simple example here, but we're going to start to do a little more complex ones. So for B, We want all of the elements in the third column. So we're going to reference our matrix D. And I want to get all of the basically rows in that third column. Did I suppress this? Yeah. Okay, so I want to get all of the rows in this third column. So I want this entire column here. Okay, so I'm going to do colon and then comma 3. And I think this was, yeah, someone brought up in Discord yesterday that I kind of swapped it in my solution. So I'll update the solutions today. Basically, I put a 3 comma colon, which would get basically do the reverse. It would get all of the columns instead of the rows. But anyways, if you submitted it kind of like I had in my homework, it doesn't matter because homework is based on completion. But what we want to do here is get all of the elements in the third column. So basically all of the rows in that third column. And when we want to get everything of something, so either all of the rows or all of the columns, we use the colon right there. All right, and then in this case, we get every single row that's in column 3. All right, next thing we want to do rows 2 to 4 and columns 3 to 4. So this will be rows 2 to 4. So we're going to be starting here, and we want to get columns 3 to 4. So we kind of want this like matrix right here. Okay, so we're going to reference our matrix D, and then we're going to look at rows 2 to 4. So we can just do 2 colon 4. So that'll give us the range of 2 to 4. And then we want to look at columns 3 to 4. So we can do that. We can run it, and then we get that little matrix that we talked about. So that's rows 2, 3, and 4, and columns 3 and 4. Okay, so now we're in the most tricky kind of question for this question, and that's when we have array addressing, which in this case we want rows 1 and 3. So I can't use the colon operator this time, because that would take rows 1, 2, and 3. I want specifically rows 1 and 3, and then columns 2 and 3. So we have to go about this a bit differently. So again, we're going to reference our matrix D, and now we want to specify the rows that we have. So if I did 1, comma 3, and then comma 2 to 3, this would be incorrect so far. This is almost like we're doing array addressing for a multi-dimensional array, because we have 3 arguments in here. So we have to go about this differently. So we want rows 1 and 3. So we're actually going to use our square brackets. So we're going to put 1 and then comma 3. And Matlab is going to treat this entire thing as one argument because we had those square brackets. Okay, so this will get rows 1 and then row 3. And then we want to look at columns 2 and 3. So I can do it this way, and I'll show you another way in a second. So let's run this, and let's make sure that we did this right. So we have rows 1 and 3, and columns 2 to 3. So we want 10 and 34, there we go, and then 66 and 303, and we have that. So I could have also done this second part here, kind of like I did in the beginning over here. So I can also do, I can put this in brackets, and do 2 comma 3, and that would give us the same output. Okay, so any questions on that? Okay, and then we'll do one more quick example here, which will be array addressing for multi-dimensional arrays. I'm actually not gonna, I guess I can. So we'll do problem 10. I'm just gonna make the same multi-dimensional array here, but I'm gonna do different array addressing. Okay, question. For C, I didn't use colons. Would that be marked off? No, it wouldn't be marked off. So if you still got the correct answer and you didn't use colons, these colons in part C here, I know it wouldn't be marked off. Okay, so yeah, in Matlab, there's often different ways to achieve the same thing, and unless I specify that you have to do it some specific way, then if you get the correct answer, you're still going to get full points. Okay, so we first want to make our multi-dimensional array here. So G, and that's going to be consisting of these three matrices. So basically A will be the first layer, B will be the second layer, and C is going to be the third layer. Okay, so I'm going to make these really quick here. -7. Okay, there we go. I'm going to suppress this up here. Suppress this. Okay, so first thing we have to do is create our multi-dimensional array. So did I specify here? No, I didn't. So here I didn't specify whether you had to make it using the cat command or if you were going to use that matrix extending kind of method. So in the quiz, I actually do specify which method you should use. And it's going to be the cat command. I'll just tell you now. So using the cat command, we can start out just by having all of our three matrices here. And then on just one line, we can make our multi-dimensional array. So I'll do G equals cat. And remember the cat command, it stands for concatenate. So by itself, when you concatenate something, that doesn't just mean you're going to be using it for a multi-dimensional array. You might be using it for vectors or for matrices to concatenate them. And that's when we have, either dimensions of 1 or 2, which we went over last class. But here we want to make a multi-dimensional array, so we're going to use a dimension of 3. Okay, and then after this, we're going to tell Matlab which matrices we want to put in this multi-dimensional array. So that's going to be A, that'll be the first layer. Then we have B, that's the second layer. And then C is the third layer. So if we run it, then here is the multi-dimensional array. Okay, so here we go. We want to display the element in the third row, the second column, and the first layer. So array addressing with multi-dimensional arrays is very similar, right, to array addressing that we just did up here for one specific matrix. But now we're just adding on the component of which layer that we want to reference. So we're going to do A equals G. That's our multi-dimensional array. We want to look at the third row and the second column. So that's very similar to actually even to what we did on line 18 here. So we're going to do 3, 2. So that'll mean the third row and the second column. But now we have to tell Matlab which layer we want to look at. And so in our question over here, it says look at the first layer, which is matrix A. So we're going to put in a 1. And if we do that, then we get a value of 9. And we can confirm that just by looking over here. That's the third row and the second column. Or we can even scroll up here. There it is. Okay, so that's what we're going to do for review. So I think this should also prepare you a little more for the quiz today. But before we get back to element by element operations, are there any questions? Okay. So let me close out of that. Continuing element by element operations. Okay, so I'm not going to go over, everything that we went over last time, but I'm going to start off with element by element operations when we are multiplying a scalar by some matrix. So we'll just talk about this here. So for this, we could either multiply our scalar. I have a different slide. Oh well, this is fine. So we can either multiply our scalar in front of the matrix or after the matrix, and it would still work out. So let's make some very basic matrix here. 0, 2, 3, 4. Alright, so here's our matrix. And if I want to multiply this by a scalar, I can do, we'll do 2 times a. And if we run that, then our answer is going to be 0, 4, 6, 8. So that works. There's no error. And I could also, let me just do that. I could also flip the order and do a times 2. And that'll also work. Let me change this here. Oh, I had a different a that was not suppressed earlier. Oh, no, never mind. I was looking at the wrong thing. Okay, there we go. Okay, so we could flip the order and we would get the same answer. Let me do that. So you see that both A and B, they have the same matrix that was created by multiplying 2 times our matrix A that we had. So the order here didn't matter. We got the same result. But this changes when we do scalar division with a matrix. Okay, so if we have the same matrix, we'll just keep it. If I divide by a scalar, the order actually does matter this time. So let's do, I'm going to do a underscore 1 equals a divided by 2. So if we run this right now, then that works correctly. We don't have any error here, so this works out. But if I do a underscore 2 equals 2 divided by a, this time we are going to get an error. So it says matrix dimensions must agree. So if I wanted to actually kind of do this operation here, where I would do 2 divided by every single element in the matrix A, which would create a whole new matrix that has a size of 2 by 2, I would then need to make sure that I specify that we actually do want to use element by element division, which, remember from last time, to explicitly state that we want to do some operation element by element, we have to put a period before that operation symbol. So if I change it to this, now we do get our matrix here. So of course, this first entry is infinity because we are doing 2 divided by 0. But yeah, so that's the difference. So for scalar multiplication with a matrix, we didn't have to explicitly state that we were doing an element by element operation. But once we get to division, it was treating 2, Matlab is treating 2 from the get-go. If we have this line here, it's treating 2 as if it's a matrix, and it's of course a scalar, and because of that we had the error when we try to run this code. But we want to actually tell Matlab explicitly that I want to do this this division element by element. So I want to do 2 divided by 0, and I want to do 2 divided by 1, and 2 divided by 1.5, and 2 divided by 2. It's for this matrix up here. Sorry, I was looking at the wrong one. So we want to do 2 divided by 0, 2 divided by 2, 2 divided by 3, and 2 divided by 4. So again, that's why we have to explicitly tell Matlab that we want to do it element by element. Okay, so that's a little review on that part, but we're going to continue on here. So element by element, we're going element by element. So we're going to have a little more visual representation for this now. So here we have two different row vectors. I think this is where we actually left off last time, but I want to go over this again. So instead of typing out element by element every time, I'm just going to put EBE. So that stands for element by element. All right, so we have two row vectors here. We have A equals 1, 1, 2, 3. And we have B equals 0 to 5. So if I want to make a new row vector here, C, where we are going to multiply these row vectors element by element, then I can do that. So first off, what I'll do, and I think we talked about this last time, but you might intuitively do A times B without the period. And if we run this, we're going to get an error here. So what Matlab sees initially, it sees that I'm trying to multiply two row vectors, or actually even more general, I'm trying to multiply two vectors here, A times B. And it gives us an error. So it first assumes that we're doing matrix multiplication. But in this case, we want to do element by element. So we're actually not doing matrix multiplication, which would require the sizes here to be different. Basically, the amount of rows in A would have to be the same amount of columns in B. Actually, I flipped it. It should be the amount of columns in A should be the same amount of rows in B if B was a column vector. And we're actually going to talk about this once we get to matrix multiplication, which will probably start up next class. And again, really quickly, this is why it kind of bugs me that linear algebra isn't a prereq for this class, because some of these topics you would understand a lot better if you took linear algebra, but I'm going to do my best to explain it. So anyways, that's why we get this error here, because MATLAB thinks we're trying to do matrix multiplication, but we actually want to do this element by element. So I want to do 1 times 0, and then 2 times 2, and then 3 times 5. So we have to explicitly tell MATLAB that we want to do it element by element. So we're going to put in that period. And now once we run this, it actually works out. Okay, so for vectors, this should say array size. For vectors, the size of the array, or the size of the vector, has to be compatible if we want to do element by element operations. So basically what I mean by compatible, it means that the sizes have to be compatible. I'm going to use quotes really quick here, but you'll see in a few examples what I mean. So the size doesn't have to be the same. So here we have two vectors again. We have A and B, and the size for vector A is a 1 by 3. So we have 1 row and 3 columns. And the size for vector B is 3 by 1. So the sizes are actually different. You know, the dimensions there are different. The magnitude is the same, but the dimensions are different. But even though they're different, we can still actually use element by element multiplication. So you'll see here that this is going to be kind of funky, at least from what you might initially think will occur. So we'll do 0, 2, and 4. That's our row vector. And then we have B equals 1, 2, and 3. Alright, so if we want to do element by element multiplication here, we're going to do C equals A times B. And I'm kind of curious actually. Everyone put in the chat what you think the size would be. So what will be the resulting size? How many rows and how many columns should we have for C? If you don't know, totally fine, because it is kind of weird. Okay, well I guess people know. That's good. Okay, so if we run this, yeah, we get a 3 by 3. So at least when I first learned this, I thought it was pretty weird. Especially if you take linear algebra. If you see these, you see that we have a row vector, and then we have a column vector. If you do matrix multiplication, the size would be different, right? But we want to do element by element multiplication. So what's actually kind of going on behind the scenes here is we're doing is 0 times 1, and for the first row here, so we're doing 0 times 1, and then we're doing 2 times 1, and then 4 times 1. So then we get our first row here. And then we're going down basically another row for B. So now we're doing 0 times 2, 2 times 2, and then 4 times 2. Then we're going to go down another row, and then we're doing 0 times 3, 2 times 3, and 4 times 3. And then we get this matrix. So we had two vectors here. We had a row vector and a column vector. And by doing this element by element multiplication, we actually got an output of a 3 by 3 matrix. Alright, so good job. A lot of you got that. I definitely would have not guessed that before. Okay, so what if we add another row to B? So now we're going to have a 1 by 3 column or row vector A, and then we're going to have a 4 by 1 column vector B. So I'll actually call them something different now. So let's do U equals 0 to 4. And then we have V equals 1, 2, 3, 4. Okay, so again here the sizes are totally different now. You know, even the magnitude is different. We have a 1 by 3 row vector A, and then we have a 4 by 1 column vector B. But even still, we can do the same kind of thing here. So in this case, we're going to get a 4 by 3 matrix. So we're doing basically the same thing that we did in the previous example here. Oh, that should say row 3. Sorry about that. But we just added a whole new row. So we're going to be doing, you know, all of this here. And then we're going to continue on with the new row in this vector here. So we're actually going to do 0 times 1. Or sorry, 0 times 4, and then 2 times 4, and then 4 times 4. And then we're going to get that bottom row here. That should be a capital C. Okay, so we have R equals U times V. We're doing it element by element, so we put in the period. And if we run it, now we get our 4 by 3 matrix. Okay. So now let's do it for matrices. So element by element, all of these should have said multiplication. Just to be specific here. So element by element multiplication for matrices. So again, if you've taken linear algebra, currently you have to kind of throw aside the idea of matrix multiplication. We're going to get to that later, but what we're doing now is, you know, totally different because we're doing element by element multiplication. Alright, so we have two matrices here, capital A and capital B. So let's make them. We have 1, 2, 3, 4, 5, 6. And then B is 2, 2, 2, and 3, 3, 3. Alright, so as the name implies here, and I kind of almost, I don't know, ironically, I think it's easier to see what would be going on here versus, you know, our last two examples. But we're going to be multiplying these two matrices element by element. So you can, if you guys already got the last few examples, I'm sure you'd understand what's going to go on here. So we're going element by element in these matrices for multiplication. So we're going to do 1 times 2, that'll be 2. 2 times 2 is 4. 3 times 2 is 6. 4 times 3, 12. 5 times 3, 15. 6 times 3, 18. So we're just going, you know, element by element. Great, straightforward name. Alright, so let's do this though. We'll do C, capital C equals A times B. We're going to specify we want to do element by element, so we put in the period before the multiplication sign. And we run it and we get our result. So you should pay attention because there is something important here. Our matrices A and B, each of them had a size of 2 by 3. We have 2 rows and 3 columns. And the output that we got was 2 by 3. which would make sense because we're doing it element by element. So for element by element multiplication with matrices, the size has to be identical. So for vectors, we just saw in the previous slides here that they don't have to be identical. They had to be what we called compatible. So in this slide here, we had a size of 1 by 3 and a 3 by 1. The sizes were different, the magnitude was the same, and we could do element by element multiplication, and we got this 3 by 3 matrix here. Then in the other slide, we had a size of 1 by 3 for A, and we had a size of 4 by 1 for vector B. So here the sizes are different, and the magnitude is also different. But that didn't matter. We could still run this, and we got our output of a 4 by 3 matrix. But if we're doing element by element multiplication with matrices, the sizes have to be exactly identical. Basically, if we had a whole new row in one of these, which should be, this slide here, if I add a whole new row in matrix B, Matlab is it'll be able to do the multiplication for these first two rows, element by element, fine. But it's gonna get to this like phantom, it's gonna look for a third row in row A, and it's not gonna see it. So it can't continue its element by element multiplication for what, doesn't exist in matrix A here, but does exist in matrix B. So if we try to do this element by element multiplication, we're going to get an error this time. So let's just show this. Size indeed matters. Yeah. Okay. So we have A equals 1, 2, 3, 4, 5, 6. And we have B equals 2, 2, 2, and 3, 3, 3, and 4, 4, 4. So if we try to run this now, we'll do C again, and we'll do A times B. Now we get this error that says that we weren't able to do it. Let me suppress this up here. So it says that the matrix dimensions must agree. So again, because we don't have our third row in A, but we do have our third row in B, we can't do that element by element multiplication because we don't have this third row in A. So to kind of recap again, for vectors, it doesn't matter if the size is different, it just has to be compatible. But for matrices, the size has to be absolutely identical for element by element multiplication. Okay, any questions on that? Okay, cool. Alright, so now we're on vectorized functions. So we've been using vectorized functions, in the class so far, but we haven't explicitly stated them as vectorized functions. So some of these functions, just as an example, would be the square root and the exponential, exp, for e. And also even trig functions like sine and cosine and tangent, all of those, they're going to be vectorized functions. So basically what that does is this function will operate on that array that we have, so it can be a vector or a matrix. And it's going to operate on every single element in that array. So the output of that operation is going to be the same exact size that we had in the beginning. So when we are trying to do an operation between these vectorized functions, we have to tell Matlab that we want to do element by element. So we're going to do an example now, don't worry. But if we, let's say we have a row vector x. So let's say we have x is 0, we have a step size of 1, and we go to 10. Let me comment this out now. Okay, so here's our row vector x. If I want to make a whole new vector here, we'll do x underscore 1. Let's do sine of x. This is going to create x1, and it's going to be the same exact size as x. Now, because of, we have a lot of digits here, so this would be like a really long row vector, but we can see in the workspace that x and x_1, they're the same exact size. So this sign function was operating on every single element in that vector x, and it produced a whole new vector that was the same exact size. So here, we didn't have to explicitly tell Matlab that we were doing an element by element operation, but trig functions are called vectorized functions, and they work element by element. Alright, so let's show vectorized functions kind of working together. So yeah, this is, well, some of these slides that I have now are from, well, all of my slides are from last semester and modified a bit to improve them. But yeah, anyways, here I have a screenshot. Usually I like to type everything out like the previous examples, but that's just for aesthetics. That's fine. Sure. Okay, so here we're going to start out with two vectors, A and B. So vector A is going to be a row vector, and vector B is going to be a column vector. So we have A equals 2, 4, 5, and we have B equals 6, 7, 8. So remember, if I wanted to do element by element multiplication between those two vectors, I could do it. Even though the dimensions are different, I can still do that operation, and it's going to create, you'll see in the end, this 3x3 matrix, just like we saw in our previous slide right here. So what I'm first going to do though is actually operate on these vectors that we have here by using different vectorized functions. So for our vector A here, we're going to use the vectorized function of square root, and for vector B, we're going to use the exponential function. And again, these functions are going to work element by element for those vectors. So I'll make a whole new vector here. I'm going to call it something a little more normal, like A_1, and we'll do square root of A. And then I'll do B_1 equals exp of B. So let's run those now, and you'll see that the sizes are going to be the same. So let's do size of A and size of A1. They're both the same, and that's again because we had a vectorized function. And we'll do size of B and size of B_1, and those are the same. Alright, so now from this, we're going to be doing an operation between these vectorized functions. So we have a row vector A_1 that was created from our vectorized function, which was square root. And we have a column vector B1, which was created by this exponential operator there. So I'll do A_2, or no, let's change this. We'll do, why not? We'll do corg equals cosine of A_1. And we're going to do this element by element. So we're going to do period and then the multiplication sign times sine of B1. So we're kind of even doubling down here. I'm using vectorized functions again. So remember, trig functions are also vectorized functions. They're going to operate on every single element in some array. Alright, so we're using, we want to multiply two vectors here that were vectorized, or we used a vectorized function. And we're going to get an output of 3 by 3. So, basically everything that we did in this example fundamentally is the exact same as we did back in this example on slide 66. The only difference is that we used these vectorized functions. So basically, we only used functions like square root, the exponential, and some trig functions. That's it. That's all we did differently. And those, when we use those functions, it's going to create a new array that's the exact same size as it previously was. Now, what if we did this multiplication here, but we actually didn't do element by element? Lab. Okay, so let's do this. We'll do a underscore 1 times sine of b underscore 1. So if I don't do this element by element, our result now is a scalar. And what I just did was matrix multiplication. So that was not element by element, but it was instead a different kind of multiplication that we can do with arrays. And in this case, we got an output that was a scalar. So again, that's something called matrix multiplication. So if you have taken linear algebra, which I will never stop talking about because I think it should be taken before this class, if you've taken that, you probably understand what we did here. So we had a row vector A, and we had a column vector B, and those sizes were compatible for matrix multiplication, which we're going to talk about now. All right, so basically, I'm just showing you the differences in these last two lines of element by element multiplication and then matrix multiplication. Okay, any questions? We're actually gonna do some element by element division first.
Yeah, Patrick, I have a question. So does it have to be same like length?
For element by element?
Mm, no, the vectorized functions.
No, they don't have to be the same length. So what you saw
Then
here,
which one? Then I think I'm getting confused with the other one.
yeah, so if you have a vectorized function, basically, maybe I understood your question wrong, but if I use a vectorized function, like, let me comment some of this stuff out. So up here, I use this vectorized function square root on this row vector A, and that does create the same exact length as vector A. Was that your question? So I can do length of A and the length of A underscore 1.
Okay.
And they're going to be the same.
Okay.
And then if I want to do element by element multiplication between two different arrays that had a vectorized function applied to them, so that's basically what we have on line 80 here. The lengths of the two vectors that we're multiplying, they don't have to be the same. They just have to be compatible. And that's basically what you saw back earlier when we were doing this element by element multiplication between these two vectors.
Oh, okay. So they have to be same no matter what.
They just have to be compatible because, you know, these two vectors, they're different sizes, but they're compatible.
Okay, I see.
So yeah, basically what I have in this block here, it's, you know, you could basically think of it as the same exact operation that we're doing on this slide that we did earlier. All that's different is we applied like a square root function and then some trig functions to these vectors. Okay. All right. Any other questions? Okay. Good thing I just looked at the time. I almost forgot about your quiz. So hopefully one of you would have yelled at me. So what I'll do now, actually, we'll go over one more slide here. And that's element by element division. Okay, so we're going to talk about the right division operator, which if you remember from earlier in the class is basically what I say is our everyday division that we do, you know, in life, in any math problems that you have. So this is going to work the same as element by element multiplication for matrices. It's going to go element by element. So we'll do A equals 10, 20, 15, and 5. And we have B equals 2. You know, I could put the 0 in front of the 2. That's the same as 2. I just did this to make them aligned, basically. and then we have 4, and then we have 5, and 3. Okay. And I can do element by element division by doing A, and then we specify its element by element by putting the period, and then we're going to divide it by B. Now if I run it, it basically does our division element by element. So we're going to go over this again, briefly next class, but before I let you guys go, I want to talk about or go over one question on the quiz, just to clarify it. So I'm going to pull it up first, and then I'm going to stop sharing just so I don't spoil the rest of the quiz. I know what I'll do instead. I was going to pull it up online here, but you'd see my answer. Maybe you'd like that, but I wouldn't.
Oh, do we start our quiz now or what?
Not quite yet. I'm going to explain something on the quiz. Okay, let me share my screen. Okay, so for the quiz, someone asked in Discord, it's basically 3 problems, but some of them have multiple parts. So for this last question that we have for the quiz, you're going to start out with this matrix F here, and you're going to use array addressing and other techniques that we've learned in the class, and you're going to create a new matrix G, which is going to consist of the following. So the first row of this matrix G that you're creating is going to be the first column in this matrix F. So basically, I tried to show you visually exactly what I want you to do by having these colors. So this first column in F, I want you to make that the first row for this matrix G that you're creating. So you see that right there. And then the second row of G that we are creating, that's going to consist of the first 2 rows in column 2 from this matrix F. So we have the first 2 rows of column 2, and you're going to put that right here for the second row of matrix G. And you're also going to have the first row and the third row of column 4 in this matrix F. So this is the first row, and here's the third row of column 4 in matrix F, and that's going to be at the end of row 2 in this matrix G. Okay, so I just wanted to explain why I have these colors here, but I think it kind of helps out to visually see where I want you to put which entries in this matrix F to create this matrix G. All right, so that's that. Your quiz is going to start in 1 minute, so pull it up, and good luck. You have 15 minutes to work on it once again, and make sure that you do what's easiest to you first, and you can see the point breakdown on the quiz as well. Okay, so I'm going to mute my mic, and again, if you have any questions, I will be here, but type out a question to me in Zoom. Don't use your mic because it might disturb other students. Alright, so good luck. I'm going to mute my mic and take off my video too.